Imagine for a minute that you take all of the atoms and all the particles out of a space. Okay, so in theory it's empty, correct? All the way down to a quantum level, there is nothing inside of that box. Well, it turns out that at a quantum level, that's not quite true. At a subatomic, or smaller than atom level, there are many particles which have distinct energy levels. These energy levels cannot be divided past the point that they are already at. These levels are referred to as quanta. In order to understand quanta, we need to first understand photons. Photons are created through what's called electron excitation. When you heat up atoms in some way, the electrons get excited and they bounce between orbits. When an electron jumps from a higher orbit to a lower orbit, it emits a wave. And this wave, this light wave, is known as a photon. Where it gets a little complicated is when we start talking about the electrons jumping between orbits. Because it seems that while the electrons are jumping, they aren't actually passing through the space between orbits. They seem to disappear at one orbit and appear in the other orbit. And this is because of their quanta. Scientists measure the quanta of subatomic particles using what is called Planck's constant. Now, Planck's constant is an equation which describes the relationship between a particle's energy level and its wavelength. In order to understand the relative size of the quantum universe, you need to look at the size of a single Planck. Now, one Planck is equal to 6.62 times 10 to the negative 34th. That means that there is a decimal point, 33 zeros, and then the number 662. To put that in perspective, an atom has a value of 1 times 10 to the negative 10th. And you can fit over 5 million atoms on the head of a pin. Now that we understand Planck's and quanta, we can begin to answer the question that I posed at the beginning of this video. We need to begin by setting aside one of the basic rules that you've learned in all of your science classes, and that is that matter cannot be created or destroyed, because at a quantum level, it's just not true. This revolves around what is called the Heisenberg uncertainty principle. The Heisenberg uncertainty principle states that at the quantum scale, it is possible for energy to be created or destroyed out of completely nothing. In order to understand this concept, look at this cup right here. Now take every single particle out of this cup. In theory, it should be empty. But if we zoom in to a quantum scale, so right now what you're looking at is the smallest quantum reality. We see all of these things bouncing around in there. That is actually matter. Now you're probably thinking right now, how is that possible? We took all of the matter out of this. But according to the Heisenberg uncertainty principle, matter can be created from nothing as long as it disappears quickly. So in theory, inside of this cup, which holds nothing, there is incredible amounts of activity. Imagine a glass of root beer, very foamy at the very top. Those bubbles that are coming up and popping at the very top can be referred to just as the matter that is being created and destroyed in the blink of an eye at the quantum level. For this reason, many scientists refer to this as quantum foam. One of the main ways that scientists know that quantum foam exists is how it interacts with photons. Now, if two photons left a specific location at a certain time and were going towards the same location, they would, in a vacuum, get there at the same time. But because quantum foam exists, each photon would need to navigate their own different path, and so they would arrive at different times. So that's it. That's the basics of quantum foam, one of the main building blocks of all quantum physics. And it only took a few minutes. All we need to do is understand some basic concepts such as quanta and Planck's, and it wasn't even that challenging.